name is Michael Hansen and welcome to this video where I will try to address some questions. First of all, it has come to some people's attention that I myself has made a mistake on one of my videos, actually the first video I produced, the infamous 300 miles per hour plus 900 miles per hour equals the 1200 miles per hour. I would argue that it is not a grave mistake, but nevertheless I will amend my my undeed here today, amend my deed. Alright. The general topic for this video will be the inertial forces that we have here on Earth. So there's been a debate going on one of my videos where I have discussed with a person that we can treat the Earth as an inertial frame of reference. To be fair and honest and true, we can't treat the Earth as an inertial frame of reference. It is a rotating frame of reference, and hence we have to apply, in essence, the inertial forces, the Coriolis force, the centrifugal force, and all those kinds. Also the Euler force, Euler force, as we call it here. But nevertheless, I'm going to show you that we can, in actual sense, when we're dealing with things here near the Earth, it is okay to treat the Earth as an inertial frame of reference, as a true frame of reference, and then use the normal laws that we have for physics. I can say sort of in a short notion that the inertial forces came to be when the Newtonian laws were derived, not in an inertial frame of reference, but a rotational frame of reference. Then additional forces came out, as I said, the Euler force, the centrifugal force, and the Coriolis force. In this video I'm going to deal with the Coriolis force and the centrifugal force, and then of course I'll also make up for my mistakes in my first video. Try to it at least. Alright, so let's get started. I'll just get my papers. Alright. Yeah. First, let's put up the Coriolis force. Or effect. First, I'd like to introduce some values that we're going to use. In this video, I'm also going to try at least to not talk not to talk to the whiteboard, but talk to you. But it's an old habit, so maybe won't get around it this time. Alright. So here we have what is called the Coriolis parameter. F is equal to 2 times omega times sine to phi. Sinus to phi. Where omega is the rotational speed of the Earth in radians, 7.3 times 10 to the minus 5 radians per second. We also have phi, that is the latitude where we are on the Earth. So let's take some examples. Let's say the equator, that's 0 degrees. Then the infamous Los Angeles International Airport, or LAX, is positioned roughly at 33 degrees. That's what I can find out. Then where I am, roughly 51 degrees in Denmark. me. And then finally we can say that the North Pole is at 90 degrees. Just so we have an idea of where we are with respect to phi. And also let me put up a drawing just right now. We're going to use it later on. Here we have a very hideous sphere. Sorry, I'm not that good at drawing. Up here we have the omega vector. And then we take some point out here on the sphere and say that this angle here, the latitude is phi. At this point we can invoke three vectors. We can invoke then one vector northwise, that is y equal north. Then we can invoke another vector eastwise, that is x. And then finally we can invoke a third vector, that is c or z, which is equal to u. So we have north, east, and then u on that point. We're going to lose that. We're going to use that later on. Now these are all vectors, of course, and phi is not a vector, that's an angle. Alright, so what we have is, we have a sphere here, could be Earth, that rotates. So we have the angular velocity here, omega. Then we also have, let's say that the tangential velocity here is this little omega here. It's sort of an angle that shows that it's rotating this way. And then we choose a point on the sphere that is phi angles up. So if we chose the equator, then we would be down here. If we chose the North Pole, we would be up here. LAX would probably be something like that. My position would be something up here, probably. Alright? And then we decompose any direction that we have in this system into three vectors, x, y, and z, or z, where we say that the x direction is eastwards, the y direction is northwards, and the z direction is upwards, so u. Alright. This is also helps to define the problem that we are trying to address, but in this moment we're not going to use this drawing specifically. Alright, so let's try to calculate the Coriolis parameter for some of these numbers here. Alright, so for the equator it's fairly simple. Sinus to phi, sinus to 0 degrees, that's 0. So the Coriolis force, or the Coriolis parameter at the equator is equal to 0. The Coriolis parameter at my position, me, is equal to 1.13 times 10 to the minus 4. The Coriolis parameter at LA, Los Angeles, is equal to 8.16 times 10 to the minus 5. Alright, so I'd like to introduce another value, another parameter, which we call the Ruffs parameter, or the Ruffs Pvalue. It's given by R0 is equal to U over F times L, where U is the velocity of a given object that we're testing, and L is the distance that it travels. So for example, if we have a baseball pitcher throwing the baseball, L would be the distance the ball travels. If we have an airplane taking off from LA to LAX to JAX, L would be the distance traveled by the airplane. But for a storm system, for example, L would not be the distance traveled by this storm system, but rather the physical extent of this storm system. How much the storm system extends over, or the low pressure or high pressure. Yeah, you get the idea. Alright, so let's take the U and L value for a typical airplane going from LAX to JAX. So I found that the cruising speed for a typical airplane, let's take a Boeing 747. The typical cruising speed for 747 is roughly 900 kilometers per hour, which is somewhat like 250 meters per second. And the distance from LAX to JAX with this 747 is roughly 3,500 kilometers, and that is 3.5 times 10 to the 6th meters. Alright, so the Ruffs Pvalue for this Boeing 747 R0 747 is equal to, well, it's 250 meters per second, and we use the Coriolis parameter for LA, so that's 8.16 times 10 to the minus 5 times 3.5 times 10 to the 6 meters, and that gives 0.87, like that. Alright, so let's remember this number. I'm going to erase. I have them on my paper, you can hopefully remember them. We're going to use them later on, so I'm going to put them up again. But let's just calculate the Ruffs number for a typical baseball instead. So in this example here, let's just say that the baseball, the pitcher is throwing in LA again. In this example here, I've said that the baseball pitcher throws the ball with a velocity of roughly 45 meters per second over a distance of 20 meters, and that gives us again the same 45 meters per second divided by 8.16 times 10 to the minus 5 times 20 meters. That gives 27,573. So let's put a box around that as well. The Ruffs number shows the relation of the Coriolis force with respect to the other inertial forces. So if the Ruffs number is very large, almost 28,000, that's pretty large, then the Coriolis force is insignificant compared with other forces, but inertial forces. But if the Ruffs number is relatively low, then the Coriolis force has some significance. So from this initial calculation here, we could conclude that I was wrong and other people were correct, because you can see that the Coriolis force do have some impact on an airplane flying, for example, from LAX to JAX. So let's expand this calculation a little bit. let's introduce what we are actually really talking about. Just going to put in the if numbers down here. That was 1.13 times 10 to the 4, and if LA was 8.16 times 10 to the minus 5. Just so that we have those numbers. Let's introduce now the Coriolis acceleration. What this is really about. It is AC is equal to minus 2 omega vector crossed with V, which is a vector. All right. So already here we have a new identity that we need to analyze. We have a cross product. So let's start by defining what is a cross product. So let's take a normal example of a cross product. We take that we have the vectors A given by A0, A1, A2, and we also have B given by B0, B1, and B2. X, Y, and Z components for both of them. So the cross product between A and B would be defined as such: I hat, J hat, sorry, I need some more space, J hat and K hat, those are unit vectors. Then we put in A0, A1, A2, B0, B1, B2. So one way to define the system would be to try to get it into a simpler form. And one way to get it into a simpler form is to block out the things that I want to calculate. So let's say if I want to calculate for I hat, I block out I hat, and then I do the following. I put in A1, A2, B1, B2, I hat minus, and then I do the same thing, but in this case I'm going to use the eraser because, as you can probably see, so that would be like this, but I'm going to keep it out. So we get for J hat, we get A0, A2, B0, and B2, J hat, and finally plus, running out of space, I'm doing the same with K, so I get A0, A1, B0, B1, K hat. And now I have the ability to solve this as I would with a normal dot product. The idea from the dot product, that is this times this minus this times this. So what would I get? I get A1, B2 for I hat, get A1, B2 minus A2, B1, I hat minus, here do the same. So I get A0, B2 minus A2, B0, J hat plus, finally the same thing here, A0, B1 minus A1, B0, K hat. There's another option. If you want the magnitude, then you can also solve A cross B as the magnitude of A times the magnitude of b times the sine to the angle theta between them times a normal vector. But we're not going to use that today because we want to solve this calculation here, so that we want to solve the Coriolis acceleration, so we get it in component form. All right. So now take a look at this. Now we have the ability, the solution to how to solve this cross product here. We have, I'll put in the components in a little bit. All right. So for the Coriolis acceleration, we said that omega is defined as, well, let's just put it like this. 0 cosine to phi, sine to phi, omega, and v. Remember that we changed the numbers here so that x is east, y is north, and z is u. So we get that the v vector is v east, v north, and v u. All right. So in essence, you can say that we have -2. Now the 2 is not a part of the cross product, but in essence what we want to find is the cross product of minus omega crossed with v. So we did as we did before. We put in I hat, j hat, k hat, and then we put in the value, so we get 0 cosine to phi, sine to phi, but remember the minus, it's minus. V, we put in VE, V north, VU. And then we do the same as we did before. I'm not going to blank it out like I did before, but in essence we get, I'm also not going to do the middle calculation to reduce it, because I found that it's actually easier just to calculate it as it is here, blank out, and then calculate the dot product method. But in this case we get, what did we do? We took this times this minus this times this. Alright, that's what we're going to do in this case here. So we get minus VU, let me just check it. Yeah, it's because it's like this, right? But I'm going to move them around so they look a little nicer. I could write them the other way, so I said minus cosines times VU, but I think it's more appropriate to say VU times minus cosinus, even though I do it the other way around. But in any way, we get minus cosine, we get cosine to phi plus Vn times sine to phi I hat, because in actual I have minus Vu times cosinus to phi minus Vn times sines to phi, and minus times minus, that's plus. Alright, so we get a minus here. Then we blank out j, so we get V0 times Vu, that's 0, minus, which is actually plus, because again we get minus times minus. So Vu, let me just check, yeah, so we get Ve times sine to phi, and then plus. Then we blank out, Let's do it the right way. J hat plus. Again, we blank out. Now we want K hat. We just make this a little better K. We blank out K hat, so we get 0 times Vn, that's 0, minus, that's plus, Ve times cosine to phi, K hat. So let's put it into component form. I'm going to rearrange this so it becomes Vn times sine to phi minus Vu times cosine to phi. I can do that, that doesn't matter. Then I get over here, I get plus, but I have a minus here. So I get minus Ve times sine to phi. And down here I get plus and plus, that's plus, so I get Ve times cosine to phi. Here you have it. Here you have the x, y, and z components of the Coriolis force on Earth. Now remember, at this point I would like to introduce some simplifications. Let's erase what we have here and just put up the form that we have, that we have just found. But because there's more to it, right? So we get that the Coriolis acceleration is equal to 2 times omega times Vn sine to phi minus Vu cosine to phi, yes, minus Ve sine to phi and Ve cosine to phi. All right. So let's think about a traditional airplane. When a traditional airplane is flying at cruising speed, I would argue that it is reasonable to assume that the airplane doesn't move upwards. It stays at the exact same position. But nevertheless, let's try to take a little more precise look at what happens in an airplane. So with an airplane, I'm just going to make it as a dot. When an airplane is on the ground, standing still or not moving, we have just one force, the force of gravity. And then we have the force of the wheels and all that keeping the plane up. But when the airplane starts to move, then we get a force here. We call that force thrust. What that would do is that it will increase the value of this vector here, because as the plane moves forward, air begins to move in over the wings, creating lift. So we call this force here lift. So as the airplane accelerates, because we have the thrust, it generates lift. And when the lift, as you can see here, is bigger than the force of gravity, the airplane will take off. Then as the airplane levels out, this force here from the thrust will still make it accelerate, but as it do that, another force comes into play, the drag force. And at some point when the airplane is at cruising speed, the force of the drag will be equal and opposite to the force of the thrust, and also the force of the lift will be equal and opposite to the force of gravity. So in essence, no net force is acting upon the airplane, and hence it moves with constant velocity. Alright, so we have that in place now. So let's look at some values for an airplane. First of all, notice that this is an acceleration. So if I wanted the Coriolis force, I could simply just make it 2m omega crossed v. Then we have the force. I actually just put an m in with it here. But let's stick with the force for now. Sorry, the acceleration for now. All right. Like I said before, when the airplane is traveling at cruising speed, we can safely say that Vu is equal to 0, which in turn means that the C component is also equal to 0. Yeah, maybe I should. The C component, or the Z component, is equal to 0. So that means I can reduce this expression here to be Vn times sine to phi and minus Ve times sine to phi. And let's put in the other numbers, so we get that we actually have 2 omega Vn sine to phi and minus 2 omega, small omega, that is, I put a Ve here, Ve times sine to phi. Let's try to remember how we defined the Coriolis parameter. It was F equals, let me see if I can remember it. Yeah, 2 omega sine to phi. But here we also defined, we could also as easily have defined this omega as a little omega. And so that is why we can rearrange this part here to get Vn 2 omega sine to phi and minus Ve 2 omega sine to phi. This big omega here reduces to the smaller omega when we assume that the Earth is only rotating in one direction. All right. So what we actually have here is, let's just put this as I want it. F equals 2 omega sine to phi. What we actually get is that it is Vn minus Ve times F. And again, the force, we just put a mass in there. And there you have it. Alright, so let's remember that calculation and then move forward. Alright, so again for LAX we had F equals 8.16, we have that down there. Since we are assuming that the plane is traveling roughly from here to here, that is eastwards, direction here. We can ignore the north component of the velocity. So Vn is equal to 0. And then you only have Ve, which is equal to 250 meters per second. So we get that the Coriolis force, or the Coriolis acceleration, is equal to, remember the minus, we had minus Vn, let's put it up. AC is equal to Vn minus Ve times F. So in this case we get minus 250 meters per second times 8.16 times 10 to the minus 5, and that is equal to minus 0.02 meters per second squared. I would definitely argue that this is an extremely low number. Very low number. I forgot to mention that this is per second. Sorry. Because the initial value is radians per second. This is an extremely low number. The airplane is accelerating with less than a half meter per second squared when it flies at cruising speed. Let's take a look at some of the forces that we have on such a typical airplane. The first thing is that I found that the mass of a 747 is roughly 400,000 kilograms. So we can find that the Coriolis force is equal to 400 minus 450,000 times 250 per second times 8.16 times 10 to the minus 5 per second, and not square. Let me see if I put it out correctly. Yes, that is equal to minus 9.18 times 10 to the third Newton. So let's look at gravity. Fg, that is mg, so that is 450,000 kilogram mass times 9.81 meters per second squared. That gives 4.42 times 10 to the sixth Newton. Pretty big number compared to this one. And finally, the thrust. So I found that a typical Boeing 747 has 4 engines, each capable of producing 296,000 Newton. That is 1.2 times 10 to the sixth Newton. But at cruising speed, that typical number is roughly 25%. So it's 0.25 times this number there, 1.2 times 10 to the sixth. That is roughly 2.96 times 10 to the fifth Newton. All right, let's put a box around them. Like this. So what do we know from these numbers? We know that the Coriolis force is insignificant compared to the other forces. If we do sort of a quick rough calculation up here, you can say that, let's say that we take F Coriolis over gravity. See what that gives. Now that I can't do in my head. So let's say it's I remove the minus because I'm only looking for a ratio. So it's 9.18 times 10 to the third divided by 4.42 times 10 to the sixth. 0.02 or 0.2%. Alright, let's take a look at the thrust compared at cruising. So that would be force cruise divided by, Coriolis force over the force thrust at cruise. And that is, again, 9.18 divided by 2.96 times 10 to the fifth. That is 3%, roughly. Roughly 0.2. So as you can see, both compared now, we know that the force of gravity at cruising speed cancels out the lift speed, the lift force. So we know already now that the force lift is equal to 4.42 times 10 to the 6 newtons. Otherwise the plane would be either going down or going up. It would pitch or descend. And the same with the cruising speed. We know that traveling at constant velocity, the force from the cruise, the thrust, 2.96. We also know that the drag force is 2.96, because if it weren't, the airplane would either accelerate forward or accelerate backward, compared with the direction of motion, of course. Alright. Of course, this is a more simplified, this is a simple example. The airplane is moving due east. We could have chosen a more elaborate example where we selected both a northward and an eastward component, but the idea would be the same. We would simply have to decompose the velocity vector that we have into the northward and eastward components, instead of just having one eastward component. What more? Well, the thing is that you actually have to integrate to get a precise number here, to get a very exact number, because since the airplane is not moving due east, but it's actually moving eastwards and a little southward, we would also have to change the latitude when we are traveling in the airplane. We could do a simplified example. We could simply calculate the Coriolis acceleration every time we switched a major number. So that would be, let's say that if JAX is at 30 degrees latitude, then we calculate here at 33 degrees latitude. We calculate these numbers again at 32 degree altitude, at 31 degree latitude, and finally at 30 degree latitude. But my estimate, I would argue that this number here and this number here will not change that much significantly. So how can I argue that? Well, let's try to calculate. Let's assume, I haven't looked it up, but let's assume that that Jx is roughly at 30 degrees latitude. So let's calculate the f, the Coriolis parameter, f Jacksonville. That is 2 times 7.3 to the minus 5 times sine 2, 30 degrees. That is It is 7.3 times 10 to the minus 5 per second. So all in all, not that much. Let's put it in. I just quickly calculated it. Minus 250 times 7.3 times 10 to the minus 5. That gives minus 0.018, so roughly 0.02. All right, this minus number here means that if we have an airplane moving eastwards, then the Coriolis force would influence the airplane southwards. If we were to reverse the situation, the airplane was traveling westwards, then we would also have to reverse the number up here, omega, and then of course we'd get a minus sign more, that would give a plus here, and of course then you could say that the force is acting northwards. All right. I'll leave that in a little bit, and then I'll come back and continue. All right, welcome back. Let's try to discuss what it is that we actually saw here. So what we saw is that the Coriolis force, the Coriolis acceleration for 747 was equal to 0.02 meters per second squared. We know that G is equal to 9.81 meters per second squared. Let's take the thrust that we have from the airplane. Let's say that we are going from, let's just say that we increase the thrust to 2.96 and calculate what that potential acceleration would be. So we know that F is equal to ma. So we know that F over m would be equal to a. So we can find that the acceleration from the thrust, the potential acceleration, would be 1.2 times 10 to the sorry, not 1.2. No, let's take that. Yes, let's take that. The maximum thrust from the engine, so that would be 1.2 times 10 to the 6th Newton divided by the mass. That's 450,000 kilograms. That would give a potential acceleration at full thrust of 2.66 meters per second squared. So as you can see here, both the gravitational acceleration and the potential acceleration at full thrust is so much more than the acceleration from the Coriolis force. One other thing. So in a situation where the Earth can be said to rotate anti-clockwise, the Coriolis force or the Coriolis effect will always be to the right. That is why an airplane traveling eastwards would feel a Coriolis force in this direction. An airplane traveling westwards would feel a Coriolis force this direction, and also in the north this direction, and to south this direction. This is the exact opposite if we have a clockwise rotation. So when do we have an anti-clockwise and clockwise rotation? Now, let's say again that we have an Earth here rotating in this direction. So it's rotating like this. So we have the North Pole here and the South Pole here. So let's imagine that we could look downwards from the north towards the North Pole. We would see the Earth and everything on it rotate this way. Can you imagine that? If I take the Earth rotating like this and then I turn it, then I would get a rotation like this, looking downwards towards the North Pole. So in this case we have an anti-clockwise rotation. If we look instead at the South Pole, then we would have the rotation like this, like this. Then we would have clockwise rotation. So that's how we distinguish it. That's also why, to some extent, that the air pattern in the northern hemisphere is almost a mirror image of the air pattern or cloud pattern in the southern hemisphere. They sort of mirror each other, doing the same thing, just in the opposite direction. Alright. I just wanted to be clear on that, and that is why I said that in the north, at the northern hemisphere, when flying to the east, the direction of motion would be southwards, downwards. Is this calculation here clearly shows that there is an effect from the Coriolis force on an airplane. There is also a similar force on a bullet or an artillery shell or something like that, an unguided missile. And so when you fire such a thing, if you wanted to be a precision sniper taking really long shots, a kilometer and further out, you would have to account for the Coriolis force, because that would slightly change the path of the bullet, and over a distance of 1,000 meters, that would be significantly changed, indicating that you want to hit a fairly small target like a person, something like that. And also with an unguided missile, if you want to hit something, for example like a ballistic missile, you would have to account for the Coriolis force, because otherwise your impact point would be changed. But with guided missiles, and imagine it if you had guided bullets, you wouldn't need to account for this effect, because would only be a matter if the missile or the bullet would be able to account for the Coriolis force in the correction. So in this case here we have an acceleration of something like less than a half meter per second squared. I would argue that any airplane you can find, any commercial airliner that you can find, can adjust for this slight acceleration just as easily as it can adjust for weather patterns, turbulence, or anything like that. So the idea of airplanes not being able to land at airfields because of the Coriolis force, that's rubbish, simply said. Alright, let's take another example. Because I showed you before that I have calculated the Coriolis parameter for where I live. F at my position is equal to 1.13 times 10 to the minus 4 per second. Alright, so let's say that I travel to my parents. That is a distance of no, I don't need the, sorry, in order to calculate the. Let's say that I travel from where I live to my parents westwards. So again, I can say that the northward component is 0, but this time the eastward component of my velocity would be, let's see, 130. Let's say that I have an average velocity of 90 kilometers per hour. That would be roughly 25 meters per second. Alright, let's make the same calculation again. Again, we use the simplified form where the Coriolis acceleration is equal to Vn minus Ve times F. But this time I'm moving westwards. So I put a minus sign in front of my velocity, and then I calculate the same thing. Vn is 0, so I get that the Coriolis acceleration is equal to minus, that's plus, so it's 25 meters per second times 1.13 times 10 to the minus 4th per second. Let's calculate that. 25 times 1.13 times to the 4th minus 4. 0.00 roughly 3 meters per second squared. And since I'm traveling westwards, this would be a direction to the north. So my acceleration, let's say the mass of my car is roughly 1,000 kilograms. It's a relatively light car. I think it's 900 and something. But the force would then be, let's just say it like this, it would be 0.003 times 1,000 meters per second squared. That would be .83 newtons. 2.83 newtons. The force of gravity on my car is 1,000 kilograms times 9.82, I think it is up here, meters per second squared. (9,820 newtons). The Coriolis force on my car would be 2.83 newtons. The force of gravity on my car is 9,820 newtons. There is, I would argue, no possible way in this world that the Coriolis force, when I'm driving in my car or flying in an airplane, would have a significant impact on the direction of neither one of them. Given that the airplane, of course, can adjust its course, but it can do that, it does do that. It also have an automated pilot where you put in waypoints, so you basically just tell the airplane where you want it to go and how fast it should go there and at what altitude, and then it flies there all the way by itself. Now, of course, you need pilots because pilots need to take off and pilots need to land, and also you need to have well-trained and well-educated pilots in case of emergencies, high violent turbulence and something like that. Yeah, but let's agree on the fact that the Coriolis force in our everyday life here on Earth, basically, when we're not trying to make satellites orbit the world, orbit the globe, or send up rockets into space or anything like that, just flying about in our airplane, our commercial airliners, and driving around in our cars, walking, cycling, whatever you're doing, the Coriolis force doesn't have any impact on us. Alright. Now you might argue here that, well, yeah, but you exclude the northern part. That's true. But remember this thing, that I'm taking a total velocity vector here, the total size or my total velocity in that vector. If I were to include the northern part as well, I would have to decompose this vector into two directions, an eastward and a northward. And then of course the northward and the eastward would be less, because the combined force of them should be the 25 meters per second. Remember that. But you are correct in assuming, and also like I said before with the airplane, I will have to account for the fact that I am shifting my latitudes. But the size of the latitude, the size of the Coriolis parameter from 1 degree to 89 degrees doesn't change that much. All right. So the next thing, I would like to take a look at is the centrifugal force. Now the centrifugal force is also derived the same way as the Coriolis force. It comes from the same general calculation, but since the centrifugal force is always perpendicular to the force of gravity, it is much easier to work with. In essence, if this is the Earth and I'm standing here, then the force of gravity is in this direction, and the centrifugal force, centrifugal force will always be in that direction. Or you could say, if you put a tangent plane under my feet, then the centrifugal force will always be perpendicular to that plane. So the centrifugal force is given by Fsen M. Yeah, m omega squared times r, where m is the mass of, well, the plane or me or the car. Omega is again the rotational tangential velocity of the Earth, and r is the radius. So let's say for a fact that we redefine W as W equator times cosine to phi. Alright? And again we said that omega equator is equal to, it was 7.3 times 10 to the minus 5th, yes, radians per second. So let's check it. We would assume that at the equator we would get this velocity here, and at the North Pole we would get 0. So cosine to 90 degrees, I would argue that's 1. So we would get W equator times 1 gives W equator. The cosine to 0 is 0. So at the North Pole we would get this number here times 0, that's 0. Alright, so at least that's okay. So let's calculate W. Given I have found W for some, I think it's 33, maybe it's 30 latitude. Nevertheless, it's 6.12 times 10 to the 5th minus 5th radians per second, and that is for the plane. So I think it must be at phi equal to 33 degrees. Alright. Let's put in the mass. The airplane again, 450,000 kilograms. So the centrifugal force then becomes 450,000 kilograms times 6.12 times 10 to the minus 5th radians per second squared times, well, I didn't define the radius of Earth anywhere, but we know that the radius of Earth is roughly 6,000 kilometers. So that is roughly 6 times 10 to the 6th meters. Let's put that in. 6 times 10 to the 6th meters. And from this we get centrifugal force that is roughly 1 times 10 to the 4th Newton. Again, remember that if gravity for the airplane was 4.42 times 10 to the 6th newtons, again we can find the ratio, so we put Fsen over Fg. And this time this calculations makes much more sense, because the force of gravity and the force of the centrifugal force will always be parallel to each other but in opposite direction. And let's calculate that. Maybe we should I'll just put boxes around them. so we can easily find them. So we say 1 times 10 to the 4 divided by 4.42 times 10 to the 6th, 100, 0.23%. So for a typical airplane, of course the gravitational constant would be a little less at that altitude, but in any way, something around 0.23% is the centrifugal force of the force of gravity. Alright, but I've drawn myself there, so let's try to do the same for me. First we need to redefine the omega. So like I said, phi for me is something like 51 degrees. So let's calculate that. Put omega me, that is 7.3 times 10 to the minus 5 times cosine to 51 degrees. That is 4. Let's just say 4.6 times 10 to the minus 5 radians per second. The mass of me is roughly 100 kilograms. The radius of Earth shouldn't have changed. So, and you can see here, again here, if I put in the radius of Earth, if I put the altitude, where a typical airplane, 40 kilometers, then it would be 6,040, it would be 6.04 times 10 to the 6. It's the altitude of the airplane, I would argue, is almost insignificant in these kind of calculations. Alright, but now we have that, so we can put it in. So the force of the centrifugal force on me is 100 kilograms times 4.6 times 10 to the minus 5 radians per second squared times 6 times 10 to the 6th meters, and that is 100 times 4.6 minus 5 squared times 6 to the 6. So that gives 1.27 Newton. The force of gravity on me is roughly 982 Newton. And again, we can find the ratio. Fsen over Fg, that is 1.27 Newton divided by 982 Newton, that is 1.27 divided by 982 Newton, that is 0.13%. I would argue I would definitely argue that a force that I would feel with 0.13%. That is, the gravity, the force of gravity acts on me with 99.87% in this comparison here. I won't feel the centrifugal force. Not in the slightest. It might help me a tiny bit when I jump. A little bit. Just a little bit. But nothing to mention. Alright. So what have we found here in this part of the video? I would argue what we have found is that the force of gravity, the force from the thrust, the force of the engines, the friction of the wheels between the wheels and the concrete or the asphalt, the force of the drag, anything that you can imagine of forces acting upon me, a vehicle driving, or an airplane flying, a guided missile, anything like that, is much more significant than the forces we can find from the Coriolis force and the centrifugal force and all those other fictional forces. Now it is true that for weather systems where we have large scale movements of things moving around on large scale movements on the Earth, then the Coriolis force, which is evident when you look at satellite images of the weather, those are definitely significant. But here, with airplanes, not so much. Alright, so the final thing I would like to go into is that I have to admit, yes, I made a mistake, I calculated wrong, and now I will atone from my bad deed, right here. So let's take a look. It is about, by the way, in that sense, if any of you notice or have any knowledge about why Brian Mullins suddenly has raised his channel here on YouTube, I'd like to hear from you. Not that I have any particularly lovely feeling for him. I don't even know the man. I haven't met him in real life, or for that matter on YouTube, on Skype or anything like that. But I'm just wondering if any of you noticed why he has put a lot of effort into all of those videos he have made and then suddenly decide to scratch it all. Alright, let's look at my mistake. Let's take one example. I would like to say right now that I will still hold that Brian Mullins' calculations definitely are wrong in his first video. But nevertheless, let's take 3 examples. One where the velocity of the Earth and the velocity of the plane are in the same direction. One is where the plane is beginning to turn, so it would be something like that. And the final example where the plane has already turned. So there are 2 ways you can calculate this. In order to find the total velocity of these 3 situations here. Alright. The first is that when you have a case like this, when you have 2 vectors that are perpendicular to each other, you can invoke the vector version of Pythagoras. So that is that in this case we would have V total would be equal to the square root of Vp squared plus Ve squared. The other one is to decompose all the vectors into their constituent parts and then add the components, the x and y components, and then finally use Pythagoras again to get the total velocity. I'm going to show you how to do that. So the general idea is to use cosine and sine. So in general we can say that we can divide any vector into the x times cosine to the angle and the y part times sine to the angle. So let's take it in this example here. As you can see, both the plane and the earth has no y components. There are only x components. Let's put in. This is our coordinate system. So we can say that for VP, let's just say here that the VE is always equal to, let's put it over here, 900 miles per hour. I'm just going to use the same numbers that Brian Mullen did, but the plane velocity is shifting between 600 miles per hour and 300 miles per hour for some reason. Alright, so in this case the velocity of the plane is 600 miles per hour, so we can say that we have 600 times cosine to, let's define the angle as such that if you have a vector like this, let's call it A. In this case the angle is positive. If we have a vector down here like this, then in this case the angle is negative. So, and of course, if we put it the other way around, we can choose whether it should be negative or positive. The most probable thing would be to use the positive angle system. Alright. So in this case, we have in this direction here, so the angle is 0, so we have cosine to 0 degrees. And down here we have 600 times sine to 0 degrees. Let's find the components. Just going to be sure. 600 times cosine to 0. 600 miles per hour, 0 miles per hour, which is what I would expect. Let's try to do the same with the Earth. 900 times cosine to 0, 900 times sine to 0. Degrees, that is, not radians. And I would argue that we get 900 miles per hour, 0 miles per hour. Like that. Let's try to invoke, let's try to add these component-wise, so we get Vt is equal to 900 plus 600, 0 plus 0, that is equal to 1500 and 0. Let's just try to invoke Pythagoras on this. So we say that the total, this is a vector, the total size is the square root of 1500 squared plus 0 squared. That is also equal to the square root of 1500 squared, which is equal to 1500. Ah, it worked. Nice. Let's say, for instance, that the total velocity here, or the velocity of the plane in this case, is something like 25 degrees, minus 25 degrees. Alright, so we're going to do the same. But remember, this time we will get both an x and a y component of the velocity of the plane. The part of the Earth is the same. Alright, so v plane is equal to, and because we are in the turn here, Brian Mullen decided that we should use 300 miles per hour, so I'm going to use 300 miles per hour. 300 times cosine to 25 degrees, and down here 300 times sine to 25 degrees. And because it's going downwards, it is a minus. So let's calculate that. 300 times cosine to minus 25. That is roughly 272 miles per hour. And again we have 300 times sine to minus 25. It gives minus 127 miles per hour. We add the vectors again like we did before, component wise. So we get the vectorial part component Vt is equal to 272 plus 900, and we get minus 127 plus 0. So that would give us 1172, I think it is. Yeah, and minus 127 miles per hour. And again, here we invoke Pythagoras in order to find the magnitude, the total magnitude. That is the square root of 1172 squared plus minus 127 squared. I can't calculate that in my head, but let's try to look. 1172 squared plus minus 127 squared. That gives 1178.79 miles per hour. Alright. And then finally over here, this is where I did my big mistake. I just added the vectors without thinking. I'm terribly sorry for that, but I'll show you that I indeed can. I do master these simple calculations. So in the final part we will have V total is equal to the square root of 300 squared plus 900 squared, which is 949 miles per hour. Alright. So again, terribly sorry for my miscalculation. No, to be fair, every physicist, every engineer makes mistakes. In my master thesis, I got results that deviated from my supervisors, and even though I was happily walking around thinking, yes, I found something new. I've actually discovered new knowledge, not something that others had done before me. It turned out that I have found I have switched out x and y parts of in my calculation, in my script. So when those x and y coordinates were corrected, I got to a fair amount of extent the same mass as my mentor, as my supervisor. You can see it here. Take something. This. I hope you can see it. This part here is weak lensing. This is from my master thesis. This is the total mass from my supervisor, Claudio Grillo. As you can see here, the black part, it's going here. The total mass from one of my models is here. It's red, almost on top of his, deviates a little up here. And then the best model I got, the total mass is here. Before I did the correction, mine were something like downwards here somewhere. Alright. This is just to say and to argue that we all make mistakes in our calculations. The problem with Brian Mullins was that not only his calculations were wrong, very wrong, more wrong than mine, but his reasoning with vectors were also wrong. The reason he used, not the reason, but the reasoning he used from the vectors, the addition that he did, was terribly wrong, because he invented a new velocity on the airplane instead of decomposing the vectors correctly. Now, that doesn't excuse that I made a mistake. I'm very sorry. I have hopefully corrected it now, and perhaps we can move on to new things. In any case, thank you very much for watching.